Hi, welcome back to AP Physics C, Electricity and Magnetism. In this video, we're going to discuss, this is Unit 1, Electrostatics. In this video, we're going to discuss electric fields. So one thing to note is that whenever you have a charged particle, it will have this three-dimensional electric field that surrounds it. And that force that we talked about from Coulomb's force, the electrostatic force, is a field force. And so gravity is our other field force. So remember, electrostatic force and gravity, they behave there's kind of like a parallel in how they behave, right? The only difference is electrostatic force can be attractive or repulsive, where gravity is only attractive. Okay, so when you bring a charged particle into that field, it is going to experience the electrostatic force, much like when we enter into a gravitational field, we will experience the gravity of that central object. Okay, now the field lines that we show, like you could see these conceptually, they're vectors, right? And they behave just like we've been talking about. Opposites attract, likes repel. So we are going to put a positive test charge, right, around our central charge and see how that positive test charge reacts. And so again, because it is a positive test charge, the field lines will go away from a positive charge, right? Again, I'm just going to draw some. Remember, there's an infinitesimal amount, right, going around these. And it will go into a negative charge, right? Because, again, opposites attract, likes repel, right? And so it's like I have my positive test charge in here. It wants to flee out of that area from a positive area or from a positive charge, and it wants to attract into the negative charge. Now, so that's a single, charged particle system. If you have multiple charged particles, again, out of positive into negative, right? So out of positive into negative. Okay, so every field line that comes off of our charges here, wrong way, will go out of positive and into negative. And it's kind of like if you think about it, they'll like go around everything, okay, and match up. Now, what happens when you have two like charges next to each other? So again, out of positive and into negative, right? And because these are positive charges, they're going to repel there. Okay, and so you'll get an area, right, that kind of sits in between everything here. So I already turned off the presentation. Right here, it sits into this area that there is no electric field, right? So it's like the E field would be zero because there's no lines, there's no charge sitting in that point. Okay. Now we can determine the field strength two ways. One, we can determine it by visual looking at them. So the closer the lines together, or the more dense the lines are, the greater the E field, the electric field is at that point. The other way we can do it is we can calculate the E field, and that's just going to be simply the electric field strength is equal to the electric force, right, or the electrostatic force divided by charge. Well, it looks very similar to when we talk about gravity. The way to calculate the gravitational field strength, right? Basically, we're doing the force of gravity divided by the mass, and this is newtons per kilogram, right? So very similar. And so we can also remember Fe is KQ1 Q2 over R squared. So we can substitute that equation in for that Fe and get another equation for electric field strength of KQ over R squared, where this Q is the central charge, or the charge that you're looking for, or the E field that you're looking. The E field is caused by that central charge. So if I have a 5 Coulomb charge, That's what's going to be causing the E field. All right. Now, how do we handle parallel plate capacitors? Well, easy. Add a positive into negative, right? Opposites attract, likes repel. Okay. It even happens here at the edges. Okay. If one came off of there, it's going to come back into that area. Okay. So now let's look at an example problem talking around E fields. So you have, and they like this, they like these orientation questions where you have essentially an axis and you're going to put two charges on the axis, one there, and they both have a -5 microcoulomb charge. Okay, the one on the y-axis is 0.75 meters away. The one on the axis is 1 meter away. And so what we're going to do is we're going to find what is the E field at the origin. Okay, and remember, you're going to put a positive charge there and see how it reacts. And so the positive charge wants to go, right? Again, E field lines come out of positive into negative. So it wants to point in that general direction, which means then our total E field, right, will kind of point up and to the right. So now let's figure out the magnitude and the direction of that. So we'll call this 1 and this 2, right? So the E field caused by 1 is going to be KQ1 over R squared, which is going to be 9.0 times 10 to the 9th times 5.0 times 10 to the -6. Make sure you convert microcoulombs, right? Micro is 10 to the -6, okay? And then the good thing is they already give it to us in meters, so we don't have to do any conversion there. And so that's going to give us an E field strength caused by charge 1 of 8.0 times 10 to the 4th newtons per coulomb. Now, E2 is going to be KQ2 over R squared. This is going to be 9.0 times 10 to the 9th times 5.0 times 10 to the -6 divided by 1.0 squared. And that's going to give us an E field of 4.5 times 10 to the 4th newtons per coulomb. Okay, now that's not going to be our total magnitude because we have to find, we have two E fields at right angles to each other. And so we have to do E1 squared plus E2 squared, take the square root of that. And that'll give us the magnitude of our E field. Okay, so we do 8.0 times 10 to the 4th squared plus 4.5 times 10 to the 4th squared. And that gives us the magnitude of an E field, of the E field at 9.2 times 10 to the 4th newtons per coulomb. But this question also asks for the direction. So we go back to our thinking right angles, right? How do we get the direction? Well, we're just going to do the inverse tangent of our y value over our x value. It's going to be inverse tangent of 8 times 10 to the 4th divided by 4.5 times 10 to the 4th. And that's going to give us an angle of 60.6 degrees. So we're up here. The E field, right, has a magnitude of 9.2 times 10 to the 4th newtons per coulomb at 60.6 degrees, right, at the origin. So that is our value. That is our answer for the magnitude and direction of the total electric field. Okay, in the next video, we're going to focus specifically on point charges, and then we're going to introduce a bunch of topics in that video, and then we'll look at different charge distributions.